Okay. So, if you have these topics, the boundary condition, conservation of the mass, the other rules can be applied to the what, to the system, and so we can define any equations. But modeling system is another background for the what, for the system dynamics. Okay. In order to model the system, firstly, you must define your problem and your solution. Okay? If you don't have any problem, and so we cannot solve this because there's nothing here. Okay? And so, if you are designing any system, any mechatronic device or the design, and so we have always the what, these two things, problem and the solution. Okay? But we need to solve this with the what? With the limitations or the requirements, right? And so we need to design a methodology for the what? For this task. And so in the first place, we need to define our purpose, which is what we will to accomplish. Okay? And so, in order to design your purpose, we need to specify the basic parameters. Just like the what, the limits, boundaries, or requirements that we need to what, to complete this task. Okay? And so if you want to design a bicycle, and then we need to define to what, its dimension, its mass, or the velocity speed, max velocity speed, right? Or the what, the max or the average time that we can use this system. Okay? And so these limits, boundary, are the main parameter to the what, to design our system dynamic model. Okay? And so, as an engineer, we need to convert the whole problem. The problem, which is defined in here, right? And so, into the what? Scalable parameters. What's the meaning of the scalable parameters? Can anyone give me an example for the scalable parameters?
Like tolerances?
No, it's not tolerances. Scalable parameters. We can set the different value of these parameters. For example, unit.
A unit
We can measure.
Measurable.
Huh?
Measurable.
Measurable. It's like the, yes, resistance or the spring factor, right? If we want, or if we can model any material with the spring coefficient, and then we can apply all the time to the what, the F equal K times X, right? And so K is a scalable parameter. We can assign the 1 or 10 or 100, right? This is a scalar, so we define it right now, okay? And so, in order to do that, we need to use the math or mathematical rules to derive these equations. But importantly, we should determine to the what, the elements of this system. The spring is an element or not? Can anyone say that? Hacer? Hacer nerede? The spring is an element or not? What do you say? It is an element or not? Yes. Why? Why? Let's just think about it. Why? Just say it. Huh? Yes, it's only a part of this system, right? Okay. And so, also, we need to determine the mathematical information. For example, if you want to create an elastic body to some purposes, for the suspension system, for example, for a bicycle, and so you know that we need to add the spring, right? But if we don't have anything about the spring formulation, and then we cannot model these things because we cannot formulate in math for this spring force or the displacement, deflection rate, right? And so we need to also know the mathematical information or the theory or the physical identity, right? And so if we have a bicycle design, and so we can say that easily this we need to design the suspension for the vibration, for example. And so how can we design this spring or the elastic body by using the spring factor? And so we can look at the physical laws, which is coming from the F is equals to the K times X. And the mathematical information either is given in that formations, okay? And so we can model it, we can test it, we can condition it, okay? So if this is done, and then we need to also define the requirements, which is coming from the first definition. But as an engineer, we need to define requirements as the what? What? Yes. What's your name? Aydın.
Yes. Like mathematical.
Yes. But we can say that the force is an input, and so force input, and F equal Kx is a model or the system, and so requirements should be assigned to the what?
The boundary.
No, as an output, because we need to satisfy these conditions, these requirements. And so how can we satisfy this formation? Defining with the what? With the output. Right? So, if we have these definitions, and then we can write or generate and select to input, cause, and output effect. In the bicycle system, we have the force value to the what? To effect. And so our output must be equals to what? X, the deflection rate, because we want to remove the what? The vibration rate, which is measured with the what? With the deflection rate of this system, which is equals to the what? Hajar? X. Right? Okay. So if we design this system based on this information, and then we must sure about that to the what? To the results. They are satisfied for the limitations or the requirements or not. For example, for the vibration example, our system is restricted with the what? With the 0.2 centimeter. And so our model cannot permit this deflection if it is okay, right? And so we need to check our results coming from the what? From the simulation of the real experiments, which is given in here, okay? And so this is either satisfied or not. If not, and then we will re-improve our model. We will set to the what? Different K value, different spring factor. And so we need to design the different suspension system in here. Based on what? Based on the mathematical informations, right? But always we need to take the results of this system, or the simulation model of the what suspension system, and then we should check it if it is okay or satisfy the requirements or the boundary condition or the limitations of our system, and then we can say that this is our system. Or not, we need to re-improve or redesign our system in here. Okay? This is the basic methodology for the what? For creating the mechatronic systems, guys. Okay? And so, we have a problem and solution with the limitations and the requirements. After that, we need to give or define our purpose with the specification of the parameters, the limit, boundary, requirements. But this should be written in terms of the what? The mathematical notation. For example, 0.2 meter is the maximum limit for the vibration. Or we can use only 100 Newton to be input, for example. Okay? Or the bicycle must not exist to the what? Access to what? The 5 meter divided by second, or the velocity speed. Okay? These are the requirements, but it's always a scalar values in here, because in the math we always use the numbers to define anything. We can be sure about what our system is okay or not by looking with the what, with examine or evaluating the R results based on these numbers. Okay, and after that we should convert this problem defined into a scalable parameters like the spring factor, damping factor, mass, right? And so we determine all the elements or the subsystems, and also we should utilize the mathematical information to model these things in terms of the what? The physical rules, right? And after that we assign the requirements. For example, deflection rate as an output in our system. And so we can create the input, output, and system, and so the math help us to what? To understand the output in time, these parameters. And then we will check our results if it's okay or not. Okay? And so how we can create the example about that. For example, suppose that we have a request for designing low pass filter. Okay? There are two kinds of sham for this. Firstly, the customer requests some things in here, just like this one. The customer says that the requests, for example, the objective. If we design the low pass filter and then customer say that you must design the first order low pass filter, and also it gives us the performance specification. What is that? What is that? Huh? Max frequency, right? And so the customer says that the cutoff frequency is 1 kilohertz, right? And so handling frequency range up to 10 kilohertz, which means that our sampling rate must be equal to the what? From the Nyquist theory, just say that our sampling rate must be equal to the what? What's your name again? No. Yes. Maria. What's the sampling rate of this system in here? Just remember the Nyquist theorem. If we are dealing with what, a 10 kilohertz signal, and so we must sample it, right? And so up to what? At least twice of this frequency, okay? 20 kilohertz or bigger than that, okay? We must use it, okay? This is the basics of the signal and system lesson. And so if you are an engineer, and then the customer cannot say everything about your system, but you must understand how we can define this problem in an engineering perspectives. The customer cannot know that, because otherwise the customer can do this and you don't have any money from these guys, okay? And so also customer says that the 3 dB lower attenuation. What's the meaning of the attenuation in the filter design? Just remember the signal and systems lesson course. What's the meaning of the attenuation? Anyone knows that?
It's like gain loss.
Huh?
Gain loss maybe.
Gain loss, but the attenuation is a ripple. For the what? For the gain of the low pass filter, okay? So this is the performance specification, but the customer also gives you a physical constraint. This is a device, and so also we have some other constraints in here, just like this one. For example, component size must be lower than, for example, 0.2 times 0.2 times 0.2 volume, right? This is the meter, okay? This is a physical constraint. Or the customer says that the power consumption is lower than 20 watts, okay? Or cost must be lower than $100, okay? These are physical constraints. And so if you are trying to design this system, not just the mathematics or the system models are important parameter, but also you need to focus on to the physical constraints, right? So, and also the customer gives you expected deliveries. For example, if you design this system, customer says that you must provide us the filter design. It's the complete theory or PCB or the circuit diagram. They can request that about these things. Or expected deliveries can ask the transfer function of this system, right? Or prototype, test results, or documentation about this engineering process. Okay? So this must be given to the from the customer. And so how can we design this system based on these informations? Then for the engineering solution methods, firstly we must split into the steps to design this problem. This is a low pass filter design, but any other design, for example UAV or the autonomous car or the robot manipulator must have the same procedures. Okay, this is the simple one, but every step are the same with the what? With the rocket design, for example. Okay, you must know that. You must understand how you can split the process or the solution of your mechatronic perspectives. This is so important. Otherwise, you cannot solve easily these systems. Okay? So, we must write in the first step, step 1, problem understanding, right? And clarification. What's the meaning of the clarification? Huh? Clarification, not classification. Clarification. Clarification.
Asking questions for more detailed information.
Yes.
To make things clear.
Yes. Bilal, you're so perfect. Okay, and so if we deal with the what, the 10 kilohertz, and so we can select the FS to or 20 kilohertz. Okay, and so also we are asking about the what. We are asked to what to design the first order low pass filter, and so we can select the first order RC filter, right? This is the low pass combination. Okay, I can choose this because I know the how I can design the RC filter. Okay, and then F cutoff frequency must be equal to the what? 1 kilohertz, right? Attenuation 3 dB, and the cost $100 and 20 watt. And so we must always write this condition as a summary. Okay, after that, step 2. Firstly, we need to model this system. Modeling the system based on the what, or using math or physical laws, right? And so how we can model these things? Sketch the diagram. Anyone remember the low pass filter configuration? Is it? Do you remember that? You can say no if you don't have any remember. No or yes? Hmm? Okay. And so, okay. And so, in order to design the low pass filter, the input signal must be given in the what, the R and C, and so this is the V out values. Okay, and then these are the sketch or the modeling diagram for the what, for solving this problem. And so we can give the what, the I1 and I2. We don't have any current in here because we don't have any roots in here, just like this one. And so if we are using the conservation of the something or the currents in here, and so we must use the Kirchhoff law, right? And Hajar, I1 must be equals to the what? Huh? No. I1, it's the current, must be equals to the what? Huh? No. If you are using the Kirchhoff law, we can say that every current, the input current, must be equals to the output, right? And so this I1 must be equals to the what? I2. Okay. Guys, come on. It's so simple. Please. Yeah. And so what's the values of the I1? V input minus V output divided by R. What's the values of I2? I2 is equals to the what? Huh? No, it's not the same. Because we have the capacitance in here. And so if we have the capacitance, C times dV out dt, right? It's coming from the what? The C parameter. It's the R parameter, right? And so, if this is true, C dV out divided by dt must be equals to V in, V out divided by R. Okay? And so, in summary, we have this equation, dV out dt is equals to minus V out 1 plus RC plus V in 1 divided by RC. This is our governing equation form to what? To calculate the V out. Okay? And so, if we are consider this system, what is the input value? Huh? V in input. What's the output value? V out. Okay? And so we can write the system. And this system must obey the what? These rules in here. Okay? And so, if this is the case, and then we must use the what? The Laplace transform. Anyone knows the Laplace transform? Could you remember that? Remember that? Okay. And so, if you are using the Laplace transform, V out S plus 1 divided by RC must be equals to V in 1 divided by RC can be given in here. And so, the Laplace transform can be utilized to what? To define the system. In a transfer function approach, in the S domain, in order to remove to what? The effect of the what? The derivative or the integral values. What's your name? No, not you. Lady. No. Behind and behind. What's your name? Yes. Huh? Lavinia. Lavinia. Okay. Why do we need to use the transfer function in S domain? Signal transformation, but what is the advantage of the Laplace transform? You don't know. Okay. Just see that the f is equals to the k times x, right? If we take the Laplace transform, if this terms fs is equals to the what? The k times xs. Okay? And so, actually, we don't need to taking the transformation in here because we don't have any s. Huh? Yes. And so we can solve it easily in the time domain. But if we had any derivative or integral part, and then we cannot easily solve this equation. And so we must use the Laplace transform to remove the derivative and integral effects on this system. Just like this one. This S means that in the Laplace transform means that huh?
There's no time interfere.
Yes, there's no time, but the S means that the derivative operation in here. If we have the 1 divided by S, and so this is the integration operation. But in the Laplace domain, we just only utilize to what? The some simple S value to model the derivative. This is a huge advantage. Just like this one. And so, if we have this information, and then the V out S divided by V in. And so, this is the transfer function. In the real meaning is that for a given any voltage value, how much V out can be generated in here, in the frequency domain. The meaning of this is that. And so, if we have this one, 1 divided by RC divided by S plus 1 divided by RC. We don't have any integration or the derivative operation, just we have a one formulation in here with the parameter of the S. And so we can easily condition this parameter without using the derivative or the integral. This is why we should use the Laplace transform, Lavinia. Do you understand that? You're sure about that? Okay. So what is the meaning of S? Just tell me. What's the meaning of the S in here? Which component or the element can be modeled by the S? Huh? No. Yes, derivative. Lavinia, derivative. Okay? Okay. So, if this is the Laplace transform, and so we can analyze the frequency input values or the character based on these informations. And so just remember that we have the cutoff frequency formula, 1 divided by 2p RC, right? This is the basic low pass filter rule for defining the low pass characteristics. Is that right? Is it true or not? Maybe I am wrong. Or maybe not. You are sure about that? Is this the correct formula? Can you say, Semester, you can sign behind of this equation? Yes or no? Yes or no? Please say something. Allah rızası için yani hani 2 saattir seninle konuşuyorum. Yes. Oh, okay. Is that is right? And we can move on. And so, step 3. Parameter selection. What's the values of this FC? Just coming from the limitations, requirements, which is equals to what? 1 kilohertz. And so, pi is a constant value. R and C must be selected based on these configurations, right? For example, if you are choosing the C 100 nanofarads based on the cost or power requirement, and so this is always behind, what's the lower than the 20 watts, okay? And if we have C value in here, and so how we can calculate the R? R is equals to what? The 2p pi fc times C, which is equals to the what? We have the 1 kilohertz in here, just like this one. C is selected, 2 pi in here, and so R must be 1.59 kilo ohm. Okay? See that we have designed the low pass filter. Is that right, Lavinia? This is the design or not? Yes. Okay. Okay. So this is our design. Because the cutoff frequency is used to calculate this one, and so we determine the what? The required R and C value. This is the work of the engineer, not the customer. Some guys paid us to select this R and C value. Nothing more, Lavinia. Is that right or not? Yes, but right or not? Right, okay. And so, if we have this information, and then we need to verify the R algorithm for verify or verification of design. How we can verify the R design? Simulation. simulation. Which kind of simulation can be used to verify this design? Şu gözlüklü kardeşim, ismin ne? What's your name? Bilal mi? Sen de mi Bilal'sin? Allah Allah, karışacak şimdi. Evet. How we can verify the R system?
We can use LT splice or rotate splice.
Yes, yes. That's good. That's good. Or we can use the MATLAB. But after that, if we drive the model in the Laplace domain, we can write the transfer function, right? Just like this one. The verify to what the transfer function, because the transfer function gives us what the frequency response of these systems. Okay? And so we can define the HS is equals to the what? The 1 divided by 1 plus S time 1, 59 times 10 over 3 times 100 times 10 over minus 9. And so this is the formula of the what? The 1 divided by 1 plus SRC, right? This is what? This is the R frequency response of the low pass filter, which is given in the what? In the Laplace transform or Laplace domain. And so we can analyze every frequency component because we want to test this design based on the what? The cutoff frequency is set or not, right? Right? Bilal?
Yes.
Okay. So we can check the what, the R, or we can define the test procedure in here. What's the meaning of the test procedures? Hilal? No, not you. Arkandaki arkadaş kim? Sude. How we can write a test procedure? What's the meaning of this? How we can test it? For example, if you have a low pass filter and you want to test it, what's your road to test it? No? Okay. Yes. Huh? R? Art? Arcam. What's the meaning of Arcam? Oh, okay. But test procedure is different. For example, if you want to test to what? The cutoff frequency, right? Okay. If we want to test this signal, and so we need to apply the 500 Hz sinus signal in input, right? And so we can apply the 1 kHz signal sinus in 2 kHz sinus in, or 10 kHz in. This is the test procedure. We have the 4 different tests in here. And so this is the condition to be tested on this system, but we need to evaluate these results. The expectation must be given in here. And so if we apply the 500 Hz signal in here, what should we expect from this system? Huh? Ne? Yes, pass. If we apply 1 kHz signal, pass or not? Pass or not? Yes, it's cutoff frequency. And so just remember that the 77% decrease in magnitude must be seen in here. And so how can I know this information? Because I am engineer and I have passed the signal and system lesson course, and so I know that this is a fact. Okay, and so what about the 2 kilohertz? Pass or not? Gain loss, lower magnitude, right? And so 10 kilohertz, lowest magnitude. And so if our design is correct, and then this test procedure must be accomplished, and so we need to check these results, and so we should give the what? A tick, 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 tick. And so if you pass the whole test, and then we can say that, Lavinia, we can say that if all test is passed, it works. Yes. Okay. And so these are the test procedures, but we need to move to what the step 5, prototype and testing. Because we must write the whole test procedure in here. After that, we need to what? We need to build the MATLAB model to emulate to what? To transfer function, right? We can emulate it. And so apply the what? Test procedures in here. Based on what? The 4 conditions, which is written at what? At the previous page, right? And so after that, analyze the result. This is important, right? If we don't analyze our results, and so we cannot say anything about the system or the performance or the characteristics, right? And so if our test procedure are not done, and then we need to update the system, which means that what is the system parameter? Which parameter must be updated in this system? Lavinia, which parameter should be updated if the performance is not good? Sude, which parameter should be updated if the test is failed? Can you tell me? What's your name? Eren. Can you tell me? Just think about your engineer. Which parameter? What? And? Yes. This is so simple. Right? We must update it. Reanalyze, retest, remodel, and something like that. Okay? So we should follow this procedure at the 5 stage. And so if we have any system or any model or any question or any problem, we should define these 5 steps, and so we can split the whole steps into the part and solve at each time these steps. And then we can solve the mechatronic systems or mechatronic designs or the system dynamic equation. But in a formal methodology, step by step, we can generalize these conditions for solving dynamic problem. Firstly, we must define the problem definition, or we must define these things, and system boundaries, right? What's the meaning of this? We need to define the objective and boundaries, our limits, and also we should define the system input and output. If we have the input and output with the restriction or the limitation parameters, and then we can model it. Otherwise, we cannot, right? Because we don't have anything about the input and output. And if we don't have the input and output definition, and so we cannot model it, either using the time domain or the frequency domain or any other domain, right? We should define it. So, in the second place, we should use or create the system modeling, right? And so, dynamic model selection. For example, if you want to create the low pass filter, you must use what? The resistance or the capacitance. But if you want to design the suspension system, SUDE, suspension system, we need to utilize to what? For the suspension system. K, spring, damping, S, right? We should choose that. This is our methodology. For the what? For creating the system model, okay? And after that, we need to define or describe everything in the what? In the differential equations. What's the meaning of the differential equations? Huh? Say again.
Equation that have the parameter and its derivative or integral.
Yes, yes, yes. Or ddt in dynamic system. We should utilize the what? Derivative with respect to the time. Okay? And after that, we should model it in the what? In the transfer function domain. Either we are designing to what? The suspension system or bicycle system or rocket system or low pass filter. Everything has analogy within each other. Okay? And then we must make it the dynamic analysis. How we can analyze our system in dynamic form? Hajar. What's the meaning of the dynamic analysis? Can you say that?
Maybe like test different values for these one, see the outcomes or the outputs, the
Yes.
different inputs.
Yes. But the dynamic means that it's a time derivative, right? And so either we can use the Laplace transform in here, right? In the general form, or frequency response. Analysis means that we have a data coming from the R model. And so, if we evaluated these results based on what either the frequency response or the Laplace one or time domain analysis. For example, state space or the dynamic equation, which is solved in the differential form. Okay? So, after that, we need to give the simulation and testing, right? In order to test our algorithm, we must prepare to what? Bilal? We must prepare to different input, but which we say that? No, expectation, but the test procedure must be prepared, right? And so, if this is set, and so the MATLAB or real experiment can be done in here, right? And then we can check the results in time or frequency domain, right? And then we can decide to what our system is worked or not. Okay? And so if we had this information and then 5, we need to define the parameter selection or optimization in here. We can adjust the key parameters. For example, if you have the resistance or the capacitance value, for example, the capacitance is 1 farad, the resistance is 1 ohm, but in the real life we don't have the 1 farad capacitance or the 1 ohm resistance, but we have the low pass filter formula, and so we must check what the resistance and capacitance values in the real life, and then we must adjust our system parameter with respect to the which components are real or not. Okay, we may not set to what or select what the 100 farad, because there's no 100 farad capacitance in real life. No one produced it, right? And so our simulation result, the key parameters, must satisfy to the what the real or the reachable parameters, right? And so adjust key params, and we must also apply the sensitivity analysis. What's the meaning of the sensitivity analysis? Anyone knows that? If you are using the resistance value, for example, the 100 kilo ohm, okay? If you are running on the real experiment and then this resistance is changed. Why? Why? Huh? Who say that? Huh? Yes, temperature maybe change the resistance value in time, and so if this is the change, and so our filter specification is changed, right? Sensitivity analysis must be done to eliminate this error. Okay. So, if there is a necessary part, we can design the control and feedback system in here. In the chapter 10, we will talk about it. We can control the bicycle speed, for example. To run velocity or the motor. And we must validate every component in real life experiment. And after that, we must update our system if necessary. Okay? Okay? Huh? Yes.
In step number 4, which is the simulation, I didn't really get what is the test procedure.
Test procedure. First step. If you want to test your system, you must create the test procedures in here, just like this one, okay? And so if you want to test our low pass filter, is the 1 kilohertz, it has 1 kilohertz cutoff frequency, and so we need to test it. But how we can test it? So we must write the test procedure in here. For example, in the first place, the 500 hertz sinus signal must be applied to the filter, and so and after that evaluate the our V out results, and after that 1 kilohertz, 2 kilohertz, 10 kilohertz, and so evaluate the whole result and write the summary of this test. You must create this test procedure in a professional way. Okay?